Somewhere in the American West right now, a train is moving. It is 1.5 miles long. It weighs 20,000 tons. It is being driven by one person. The forces holding this train together and the forces threatening to tear it apart are almost beyond comprehension. And the only reason any of this works is because of engineering solutions so elegant they seem like they shouldn't be real. Let's go inside. Heavy haul railroading is one of the most demanding engineering disciplines on the planet, and most people drive over a crossing every week without giving it a second thought. 20,000 tons is not a number that fits easily in the human brain. The Eiffel Tower weighs about 7,000 tons. This train outweighs it by nearly 3 to 1. To move that weight, safely, efficiently, under control, requires mastering physics, materials science, software engineering, and 60 years of hard lessons learned the expensive way. In this video, we're going to follow a heavy haul train from throttle to brake. We'll look at how the power gets to the rail, how the train stays in one piece, how it stops, and what happens when something goes wrong. Before we talk about moving a 20,000-ton train, we need to talk about the hardest part, starting it. The entire weight of this train transfers to the rail through contact patches smaller than the palm of your hand, one per wheel. Every single pound of traction that moves this train has to pass through those patches without the wheels spinning. What engineers call tractive effort is the horizontal force a locomotive can apply to the rail. Modern AC traction locomotives can produce over 190,000 pounds of tractive effort at starting. That is roughly equivalent to pulling 60 fully loaded semi-trucks from a dead stop simultaneously. But tractive effort alone doesn't tell the whole story, because before the train moves, every slack in every coupler has to pull taut. On a 150-car train, there can be several feet of total slack, small gaps between every coupled pair. The engineer has to take that slack up gently, sequentially, or risk a violent run-in that can break knuckles, damage cargo, or derail cars. Starting a heavy train is not about raw power, it's about patience and feel. The engineer eases the throttle, nudges the train into motion a section at a time, feeling the resistance through the controls. Too aggressive, and you get what railroaders call a rough coupling event. Too passive, and the train won't move at all. Get it right, and 20,000 tons begins to flow. Here's something most people don't know. On the heaviest trains in the world, the locomotives aren't all at the front. They're distributed throughout the consist. The lead locomotives pull, a set buried mid-train push and pull simultaneously. More units at the rear push. This isn't just about adding more horsepower. It's about managing forces within the train itself. On a conventional train with all power at the front, the couplers at the very front carry the entire weight of everything behind them. The forces escalate the closer you get to the lead unit. Add power mid-train and at the rear, and those coupler forces redistribute. The peak stress drops. The train holds together more safely under conditions that would otherwise be impossible. The standard AAR knuckle coupler, the same basic design used for over a century, has a tensile strength of around 900,000 pounds. Even that extraordinary strength has limits. Distributed power keeps the forces well below those limits on grades and curves that would otherwise be unworkable. The distributed power units aren't operated independently. Every remote locomotive in the train is slave to the lead unit via a continuous radio data link. When the engineer in the lead cab moves the throttle to position 6, every remote unit in the consist responds to position 6. Simultaneously, dynamic braking, horn, bell, emergency brake. Every control action is mirrored across the entire locomotive network in real time. The engineer isn't driving 4 locomotives. They're driving one distributed machine that happens to be 1.5 miles long. The radio control system operates with response latency measured in milliseconds. On a moving train, a second of lag could be catastrophic. Milliseconds are what make it safe. But here's where the real engineering challenge begins. Because getting 20,000 tons moving is actually the easy part. Stopping it is where things get dangerous. A 20,000-ton train descending a 2% grade will accelerate under its own weight. Gravity doesn't care about schedules or stopping distances. On a 2% grade, Gravity is pushing this train downhill with a force of roughly 800,000 pounds, continuously, every second. A passenger car at 60 miles per hour needs about 200 feet to stop. A loaded heavy haul train at the same speed needs anywhere from a mile to a mile and a half. The first and most important braking tool on a modern locomotive isn't friction at all. It's dynamic braking. And to understand it, you need to understand how the traction motor works. In traction mode, the locomotive's traction motors are electric motors. Electricity flows in, wheels turn, straightforward. In dynamic braking mode, the engineer reverses the relationship. The rolling wheels now drive the motors, which become generators. Instead of consuming electricity, they produce it. That electricity has to go somewhere. It's dumped into massive resistance grids on the roof of the locomotive, essentially giant electric heaters. The kinetic energy of 20,000 tons becomes heat, and that heat radiates into the atmosphere. On a long descent, those grids can reach temperatures that glow visibly in low light. The locomotive is literally burning off momentum. Dynamic braking is most effective at mid-range speeds, roughly between 15 and 50 miles per hour. At very low speeds, its effectiveness drops off sharply. That's where the air brakes take over. In 1869, George Westinghouse invented the automatic air brake. 150 years later, the fundamental principle is still in use on every freight car in North America. The brake pipe running the length of the train is kept under positive air pressure, typically 90 pounds per square inch, when the brakes are released. To apply the brakes, the engineer reduces that pressure. The drop propagates down the train at roughly 900 feet per second, triggering a valve at each car to apply its brakes. In an emergency, a rapid full reduction triggers every car's emergency reservoir to dump simultaneously, applying maximum braking force on every wheel in the train at once. The critical insight of Westinghouse's design, the reason it's still used today, is that it is inherently fail-safe. A broken hose, a severed pipe, a failed valve. Any loss of air pressure applies the brakes. The train cannot run away due to a brake system failure. The coordination of dynamic braking and air brakes, the precise dance between them, is one of the defining skills of a heavy-haul locomotive engineer. Too much air brake with dynamic braking engaged, and you get wheel slide. Too little and the train runs away on the grade. The balance point is where experience lives. There are two forces that heavy-haul engineers spend their entire careers managing. They are called buff and draft, and getting them wrong can destroy a train. Draft forces are tension, the cars pulling on each other as the locomotives haul them forward. Buff forces are compression, the cars pushing into each other during braking or when rear power pushes harder than the front. On straight track, both forces act along the center line of the train. Manageable, predictable. On a curve, those same forces act at an angle to the track. Buff force, compression, now has a component pushing the cars sideways, off the rail. This is called stringlining. A train under heavy buff force on a curve will try to take the geometric chord of that curve, the straight line between 2 points, rather than follow the track. The cars climb the rail and derail. Stringlining derailments are catastrophic, and they happen to experienced crews on familiar territory because the physics is unforgiving. Distributed power helps manage this. By reducing rear pushing force on curves, keeping the train in draft rather than buff, the stringlining risk drops dramatically. Modern heavy-haul engineers work several miles ahead mentally. They're not reacting to the track. They're setting up for what's coming. Before a curve on a downgrade, an experienced engineer will set the train up in draft, light tension throughout, so that the curve is navigated with the train pulling slightly against itself rather than compressing. It looks effortless. It is anything but. And underneath all of this human skill and engineering hardware is a layer of technology that most people never think about. The system that watches the train even when the engineer can't. Positive Train Control, PTC, is the federally mandated overlay system that monitors every train movement in real time. Every second, PTC knows where this train is to within a few feet. It knows the speed limit for every segment of track ahead. It knows the train's braking capability based on tonnage, grade, and brake status. If the engineer doesn't respond to a speed restriction, PTC will apply the brakes itself. Not as a suggestion, as a command. The system cannot be overridden by the engineer in the cab. The physics of stopping distance is baked into the algorithm. If the math says the train needs to start braking now, it starts braking now. At the rear of the train, an end-of-train device monitors brake pipe pressure, reports rear speed and location, and can, on equipped trains, initiate an emergency brake application from the rear simultaneously with the front. Two-way end-of-train capability can reduce stopping distance on a heavy train by a meaningful margin in an emergency. In heavy haul, every foot of stopping distance matters. With all of this technology, all of this engineering, all of these automated systems, there is still a human being in that cab, and there will be for the foreseeable future. Because what automation can enforce and what physics demands are two different things. The system can prevent a disaster. It cannot optimize a run the way an experienced engineer can. The feel for how this particular train, this length, this tonnage, this locomotive combination, responds on this particular grade is knowledge that lives in a person's hands. Heavy haul railroading moves the raw material that builds everything else. The coal for power plants, the grain for export, the ore for steel, the chemicals for manufacturing. It moves it quietly, efficiently, at a cost per ton mile that no other land transport mode can match. And it does it with a level of engineering sophistication that is almost invisible to the world it serves. Next time you sit at a crossing, watching the cars roll past one by one, think about what it took to move all of that. We covered a lot of ground. Tractive effort, distributed power, dynamic braking, air brakes, buff and draft, and positive train control. If any one of those topics deserves its own deep dive, let me know in the comments. Subscribe if you want to understand how the infrastructure around you actually works. The engineering is hiding in plain sight.